Okay, today we're going to talk about limits of functions of two variables. And in order to understand this, I think it's helpful to remind ourselves of how a limit of a function of one variable works. So if you look at the picture here, there's something you might have seen from Calc 1, for instance. Okay, where as x is approaching a value x naught, y is approaching the value L. And the graph of the function is approaching the point x naught comma L. Okay? And you remember the whole epsilon delta stuff, right? Is that we ask ourselves this question. If you go to a distance of epsilon away from L, so that means, that means you're looking at a horizontal section here from L minus epsilon up to L plus epsilon, and you're asking the question, how close does x need to get to x naught in order for y to be in that band? Okay, remember that? And then what do? We figure that out. And then we call this guy down here x naught minus delta, and this guy x naught plus delta. When x is in this area, y will be in this area. That's very important to remember, okay? When x is in this area, y is in this area. Now, let's look at a function of two variables. So first of all, look at how we write it. Read this down here, okay? That's the limit as xy approaches the point x naught y naught. The limit of what? The limit of some function of x and y equals what? Some number L. That's a number there, not a point. That's a number. This is a point. This is a number. Okay? Because why? It's a function of two variables. So you plug in points x, y, you get back a number z. Okay? So that's how it looks when you write it. Now let's look at what is happening visually. It's the same idea. What's over here is analogous to this. Okay? You have your domain down on the bottom. It's just that the domain here has two dimensions instead of one. So there's an x-axis and a y-axis. Your range is here, covered by the z-axis. Okay? Now, as xy approaches the point x naught y naught, so that means xy approaches that point. Here's what's different. Let's actually take a step back. In the one variable case, x approaches x naught. How many ways can x approach x naught? Only two possible ways, from the left or the right. But now, in the two-dimensional case, it's very different. The point xy can approach the point x naught y naught in many, many, many different ways. Even some ways like this. Doesn't even have to be a straight line. Okay, so that makes this much more complicated computationally. The idea is 100% the same. The computation's much more difficult. And for that reason, we're not going to really do much computations. But nonetheless, I want you to understand that. What is this blue shaded part there? What is it? That just shows the numbers that are within a distance of delta from x naught. So that same idea is in this other picture, except, well, let me make that different here. Except instead of shading an interval on the number line on the x-axis, we're shading a disk, or what some people would call a ball, on the xy plane. Those show all of the points that are within a distance of delta from x naught, y naught. Okay, and when xy is within that disk, then z will be within this range. Or another way to say that is the point f of xy will be in this disk up here. Okay? So same concept. As the input gets close to some specific value, the output gets close to some specific value. It's just that in Calc 1, the values of the input were numbers, and here in Calc 3, the values of the inputs are points. Okay, so let me show you how the definition is written in the book. Let's go ahead and erase this picture. Okay, here's the definition right out of the book. Okay, let S be an open set containing x naught, y naught, and f be a function of two variables defined on S. Okay, so S is like your domain, more or less. Okay, the limit of f of xy as xy approaches x naught, y naught is denoted this way. That's exactly how I've written it over here. Okay, and it means what? Given any delta greater than 0, epsilon. Given any epsilon greater than 0, there exists a delta greater than 0, such that if xy is in this disk of distance delta around x naught, y naught, then f of xy will be in this interval of distance epsilon around L. Okay? Now, what about the definition of continuity? Let's go ahead and put that up here. Since we're looking at definitions, you see the definition of continuity in this setting is exactly the same as it is in the single variable setting. A function is continuous. It's just, here's the only difference. We would be saying here continuous at a point instead of saying continuous at a number. It's continuous at a point if the limit of the function as you approach that point equals the value of the function at that point. That's what means continuous. Okay, let's look at some of the rules for limits and continuity. In order to save time, we're not going to, I'm not going to say all these out loud. I'm just going to point out a couple things, okay? I'm going to ask you to pause the video and just read these rules, but I'm going to point out to you that these are just Exactly the same ideas as the limit rules and continuity rules for single variable functions. Okay, you just got the limit of a constant function is the constant. Okay, the identity rule, you might not remember that, but look at it, go ahead and read it and see what it says. Okay, it's just like it was for single variables basically. All right, sum and difference rules. I'm not talking about derivatives here, okay? We're just talking about limits. Scalar multiples. The limit of a multiple of a function equals the multiple of the limit. Products, quotients, powers, roots. Okay, they're all just analogous to the single variable rules. There's nothing new here. Same for continuous functions, okay? The sum of two continuous functions is continuous, and so is the difference. Multiple of a continuous function is continuous. Products of continuous function is continuous, and so on, okay? Nothing new here. So what is it that I want you to be able to do? Okay, let's talk about that. I do want you to be able to calculate some limits, but as I talked about before, the computations here, the concept is 100% the same, but the computations can be orders of magnitude harder because you can approach your target point from many different directions. So therefore, you're only going to be asked to find limits of functions that are very, very well behaved. Essentially, you're going to be just plugging in the target values. Okay, I'm not going to give you questions like this. Find the limit of xy over x plus y as xy approaches the origin. I'm not going to give you a question like that because this is quite a bit more complicated than it might seem. Okay? First of all, you might notice that this could be difficult, maybe, because why? Because 0, 0, the origin is not in the domain of this function, is it? If you try to plug in the origin, you're just going to get 0 over 0, which is undefined, right? That doesn't mean the limit doesn't exist. It just means it's not easy to find. Either it doesn't exist or it takes some more work to find it, okay? But I will give you questions like this. So, okay, so I'm going to cross that one out. I'm not going to give you a question like that, but I could give you a question like this. Find the limit of xy over x plus y as xy approaches the point 1, 1. Okay, now that's a very easy question. Why is that easy? Well, this is a continuous function. F of xy equals x is continuous. F of xy equals y is continuous. And therefore the numerator is a product of two continuous functions, so the numerator is continuous. The denominator is a sum of two continuous functions, so the denominator is continuous. Therefore, this function is a quotient of two continuous functions, so it's a continuous function. Since 1, 1 is in the domain and the function's continuous, then the limit will equal the value of the function at 1, 1, which is a half, isn't it? Okay. Only because I'm looking at a continuous function here do I know that I can just plug in 1, 1. Can't always do that to find a limit, but if you know the function's continuous, then you can. I could not have just plugged in 0, 0, because 0, 0 is not in the domain. Okay? And remember, things like polynomials, trig functions, log functions, exponential functions, rational functions, these are all continuous. Okay? Those are the only kind of limits that you're going to be asked to find where it says the whole limit. If I want you to find the whole entire limit, it's going to be an easy one like that. Okay? But there's something else I want you to be able to do, which is this. Let's go back to this picture here. Well, actually, let's not look at that picture. I'll just draw a new one. Let me write here what was here a few minutes ago. The limit of xy over x plus y as xy approaches the origin Okay, I'm not going to ask you that. It's a bit too complicated at this level. Okay? And the reason why it's complicated is because xy could approach the origin from infinitely many different directions, even curved. Okay, there's just too much to try to account for. It's too difficult at this level. Okay, but I might ask you something like this. Find the limit of that function as xy approaches the origin along the y-axis. So that means I'm telling you to find that limit if you approach the origin from this direction, or technically this direction. That is not difficult. Let me show you how to do that. Look at this y-axis. What's that mean? What does y-axis mean? Being on the y-axis means that the x value is 0, right? So what that means is you're really calculating this limit here. You're calculating the limit of 0 times y over 0 plus y as y approaches 0. Okay? So that would be the limit of 0 over 0 plus y. Oh, well, here, what's 0 plus y? 0 plus y is y, correct? There we go. So you're trying to find the limit of 0 over y as y approaches 0. Okay, that is an undeterminate form, isn't it? Isn't that type 0 over 0? So what would you do? You should use L'Hopital's rule. The derivative of 0 is what? 0. The derivative of y with respect to y is 1. And so our answer is going to be 0. Okay? So let's do a few more questions like that. And I'll throw in some other ones as well of the first type I showed you. So here, let's do the limit of y over x plus cosine of xy as xy approaches the point 1 pi. Okay, so let's think about this. Rational function, that's continuous. Trig function, that's continuous. So the sum of the two is continuous, and therefore the limit as xy approaches 1 pi equals the value at 1 pi, which will be pi over 1 plus cosine of 1 times pi, which equals pi plus negative 1. There's our answer. Minus 1. So that's an easy one. Okay, let's try now. Let's find the limit of 3xy over x squared plus y squared as xy approaches the origin along the line. How about if we say x equals 2y? Sorry, I meant to say y equals 2x. Okay, so what is it that I'm asking here? Let's just draw a picture here. Here's our domain. Okay, you're looking down here. Maybe I just want to make sure that you understand the whole thing about 2 dimensions versus 3 dimensions. Okay, so the function exists. Whoops, I'm sorry, I drew the wrong one. I meant to draw this one. The function exists in 3 dimensions. Here's our x, y, z. Okay. Here's our domain, is the xy plane. Okay, so when I draw this, what we're doing is we are looking straight down at the domain. Okay, I just want to make sure you're clear on that. There's no z-axis there because I'm just looking. It's like I'm hovering over the top. I'm hovering up in space and I'm looking straight down at the domain. Okay, all right, so let's just move this over here. Oops. Okay, so here's the origin. That's the point we are approaching. And it says we are approaching specifically along the line 2x. So xy can approach along any direction, even the curved direction. Okay, but I'm only asking you in this particular question, what is the limit if you approach the origin along the line y equals 2x? Okay? You can even write it like this, by the way. You can even write the limit of 3xy over x squared plus y squared. And you can literally write, instead of x comma y, you can write x comma 2x approaches 0, 0. Okay, so what that means is every y is replaced with a 2x. So we get the limit of 3x times 2x over x squared plus 2x squared. So you see there's only one variable, x. So now we just write as x approaches 0. So let's see what that limit is. So first of all, I'm going to simplify. So this would be what? 6x squared over 5x squared, right? As x approaches 0, you get the indeterminate form of type 0 over 0. So we use L'Hopital's rule. Which converts it to the limit of what? 12x over 10x. Still in indeterminate form of type 0 over 0, so we use L'Hopital's rule again. And we get the limit of 12 over 10, which equals 12 over 10, which is 6/5. And that's our answer. Okay. Now let's remember that that was 6/5. Let's find the limit of the same function as we approach the origin from a different direction. How about if we did this? Same function. Approaching the origin again. Except this time I'm going to say along the parabola y equals x squared. So let's write this in a different shade of red. If we approach the origin along one of these two paths, what limit would the function have? Let's calculate it. So I'm going to write the limit as x squared approaches the origin. And the function will then be 3x times x squared over x squared plus x squared squared. So that's the limit of 3x cubed over x squared plus x to the 4th as x approaches 0. I must use L'Hopital's rule on that, correct, because it's an indeterminate form of type 0 over 0. So that gives us the limit of 9x squared over 2x plus 4x cubed, still an indeterminate form. Use L'Hopital's rule again. We have the limit of 18x over 2 plus 12x squared. And I want to point out to you that that is not an indeterminate form anymore. What's the answer? 0 over 2, which is 0. This is interesting. Same function. Approaching the same point. The input is approaching the same point. It gives us two different values if we approach from two different directions. What does that tell you? Well, it tells you the exact same thing as, for instance, in Calc 1, if you had a function where the left-handed limit does not equal the right-handed limit. It's the same thing. It's getting different limits from different directions. What does that mean? It means the two-sided limit doesn't exist. So same exact thing here. This tells us that the limit of our function as xy approaches the origin does not exist. Why does it not exist? Because we get conflicting values if you approach the origin from different directions. So, what I want you to get from this is that, and I said this earlier, calculating limits when the input has two variables can be very, very complicated. I'm only going to give you easy ones, okay? But they can be very complicated. But it is sometimes easy to show that a limit doesn't exist, because you might be able to show that you get different values from different directions. So that's a bit surprising to some people, that showing that some of these limits don't exist is actually oftentimes easier than showing that they do exist. Okay? And by the way, before we close, let's go back up to this question that we had done here. Along the line y equals 2x. And I just want to point out to you that you can all at once just a second, let me catch up here to what I'm saying. You can calculate the limit as xy approaches the origin from any straight line direction. You can do all of them all at once by just saying xy approaches the origin along the line y equals mx. Let's do that. So I'm going to write x mx is approaching the origin. Okay, and then we'll have here 3x times mx over x squared plus mx squared. So that's the limit of 3mx squared over, it'll be m squared plus 1 x squared. As x is approaching 0. Okay. Well, I think when we did y equals 2x, I used L'Hopital's rule, didn't I? But now I realize that it's actually a little bit easier, because we can just cancel out the x squareds, couldn't we? That would have been faster than using L'Hopital's rule twice. Well, what do we end up with? We end up with 3m over m squared plus 1. That's the answer. 3m over m squared plus 1. That tells me that the limit overall does not exist, because, for instance, let me erase some of these red lines. Well, we did this one already. Approaching the origin along the line y equals 2x, then what value would you get up here? You would get 3 times 2 over 2 squared plus 1, and you get 6/5. That's what we got. The limit would be 6/5 if you approach along the line y equals 2x. But what about if you approach along the line y equals 1/2 x? Then what would this be? Then it would be 3/2 over 5/4. 3/2 over 5/4. What is that? Let's just work it out real quick. 3/2 over 5/4. So that's 3/2 times 4/5, which is 6/5 again. Isn't that interesting? It's the same limit. But we did find what? We did find that if we approach along the parabola, y equals x squared, then you get something different. What about, let's erase this here. What if you approach along the line? Let's find a different shade of red here. Well, we'll have to use orange. Let's approach along the line y equals x. Then what would this equal? In other words, m is 1. So in that case, wouldn't we get 3/2? Ah, interesting, isn't it? The limit along this line is 6/5. The limit along this line is 6/5, but the limit along this line ends up just being 3/2. So that right there tells you that the overall limit doesn't exist, because you can get different limits by approaching the origin from different directions. So I'm going to ask you to do some questions like that. Okay, but that's all we're going to do. We're not going to get any deeper than that because the calculations can become terribly complicated. All right, that's it for today.